With this project, I wanted to focus on virtual production, modelling assets for real-time virtual reality rendering using the Unreal Engine. I chose a car showroom scenario so I could focus on creating one polished asset to show off in VR. For this experience, I decided to use the new Oculus Quest all-in-one mobile-based virtual reality headset as my target platform. I chose this platform for two reasons. The first is that I wanted to teach myself how to optimize 3D assets for mobile VR, which is a very demanding platform from a performance point of view. The second is that due to the headset's ease of use and lack of setup, requiring no PC or external sensors, I could easily show my tutors the progress I was making week to week. I have since found that the knowledge I have gained regarding the optimization of models for mobile VR is also very useful when working with very high poly CAD models on PC, as in both scenarios eking out as much performance as possible is important. The initial scope of the project outlined in the previous video did get scaled back slightly during production for a couple of reasons. While the initial pitch detailed more functionality in the cabin, such as operating the indicators and turning on the lights, these features were ultimately cut due to a focus on the artwork of the car and performance limitations of the hardware. In my undergrad project, which was also a VR experience, I made the mistake of over-scoping the functionality of the project, which left me too little time to work on the visuals. I didn't want to make the same mistake again, so most of my production time was spent on the car asset itself, the modelling, materials and performance optimizations. Building for the target mobile hardware, each mesh is limited to a maximum of 64,000 triangles, and only 100,000 triangles can be shown in any given frame. There is also a limit of 100 draw calls in place. A draw call is a request from the GPU to the CPU to draw a given asset, and one draw call is generated per mesh per material. This meant that through trial and error, I came to the conclusion that grouping meshes that use the same material was the best approach, although this has to be calculated while also thinking about the benefits of frustum culling. This is where only the meshes that are on screen are rendered. The glass parts of the car in particular are very expensive to render, as each pixel has to be processed twice, once for the glass surface reflection, then again for whatever is visible through the glass. At first I combined all glass elements into one mesh to save on draw calls, but I soon found that sitting in the cockpit was a particular performance trouble spot, as the majority of the rendered view would be through the glass, leading to heavy frame drops. Even when the player was looking through the windscreen, because all the glass pieces were in one mesh, it meant the engine couldn't cull the side windows, rear windows and headlamp lenses, and was having trouble rendering it all. Once I cut the glass pieces up, allowing the frustum culling to cull any part that wasn't visible, performance improved greatly in this area. This is one example of the constant balancing act that is required when developing for mobile VR hardware. Another trouble spot that needed attention was looking forwards at the engine, which contains lots of geometry, as this view also looked through the rear window and the front window out over the bonnet. These pixels needed to be processed 4 times, resulting in a lot of slowdown. Other performance techniques utilised included fixed foveated rendering, where pixels further from the centre focal point are rendered at a lesser resolution but are unnoticeable due to the barrel distortion applied, and using a forward renderer instead of a deferred renderer to save some render time. Judicious use of texture sizes to optimise video memory, only using higher res textures where necessary, also helped maintain frame rate. These and other techniques allowed me to hit the 72 frames a second performance target most of the time, rendering at a target resolution of 1600 by 1440 per eye. Other technical speed bumps encountered included a forced Oculus Quest firmware update mid-development that forced my project to run in Oculus Go emulation mode, which lowered the field of view and limited the app to using one controller. I wasn't the only developer to be caught out by this issue. I could not work out why my shadows were either not casting or were very low quality. The solution was a combination of marking blueprints as static, checking static light sources, increasing the light map resolution, and marking meshes as two-sided for shadow casting, but this took a whole day to figure out. I made use of the free automotive material pack from Unreal, but I had to simplify the shaders for mobile, as the hardware has a limit of 4 textures per material. I also created stereo depth correct reflections for the car. In the previous video, I said I'd use C++, but quickly found most tutorials and resources use Unreal's visual scripting language Blueprint, and it could achieve what I needed more easily. I iterated through several control schemes, ultimately settling on simplified controls which were mirrored on each controller, allowing for users to use one controller only, and catering for both right-handed and left-handed players. I also added a video of the real car in the experience, so that a user may compare the model to the real thing. Support for the Vulkan graphics API for Oculus Quest was introduced to Unreal Engine late into development of the project. This would probably increase performance by up to 25%, but was released too late to be implemented. A deeper menu system and car control interaction could be implemented given more time and Blueprint knowledge. I am actually integrating similar functionality using Blueprint at my current contracting position now. The spoiler could be modelled and animated. I ran out of time and polygon budget to model the interior of the spoiler bay. Texture atlasing could be implemented where multiple separate textures are combined onto a single larger resolution texture sheet, but I'm unsure if this would benefit on mobile hardware due to the texture memory limitations. During this project, I have become much more familiar with asset creation for Unreal, particularly optimizing assets for mobile platforms. I have also become much more adept at using Blueprint to do visual scripting for functionality implementation. I am currently using the skills learned during this project at my current role as a VR engineer contractor for the United Kingdom Atomic Energy Authority, and my knowledge base continues to grow in this area. I continue to enjoy the challenges in this field and find solving them very rewarding.